Sir, Professor, Sir Ramesh Bansal, sir.
Yes, please.
Sir, it is for the PDF version or PowerPoint version, sir?
Is PDF version.
So better to type Control L, sir. It's having full slide will visible, I think. Control L. So it's not working, sir. It's Control L. Otherwise, just leave it, no problem, sir. Is it possible to zoom another 2 to 3%?
Yeah, sure. Maybe I will do that.
Okay,
we are ready to start, please.
Yes, sir.
Okay, just maybe.
Once our side's okay, we'll start the program sites, no problem. Because generally, we start the program exactly that time.
Okay.
Another 2 or 3%, it's okay, sir.
No, I'm trying to.
Okay, sure, sir. So it's otherwise it's having. Okay, sir. Yes, now it's okay, sir.
Maybe sometime the voice can be problem. Maybe can I switch off the video?
Yes, sir, sure. Yes, you switch off the video also, so it's no problem, sir. Sir, if
Then
possible to press Control plus L, it's in full slide mode will go, I think. Control plus L.
Okay, no problem. Maybe I will just. You are right. Is it?
Yes. Very good, sir. Sir, we'll start the program, sir.
Yes, we can start, please.
Yes, sir. It's a very good afternoon, sir. Professor Ramesh Bansal, sir, for accepting our invitation and delivering the lecture for the AST-sponsored Sttp program for Series D. I welcome you, sir. Mr. Sainath, sir, to introduce today our resource person, Professor Ramesh Bansal from Sharjah.
With your permission, sir. Very good afternoon, sir. Very good afternoon, Ramesh Bansal, sir. Thank you for accepting our invitation and giving your valuable time and spending your valuable time. Professor Ramesh Bansal has more than 25 years of diversified experience of research, scholarship of teaching and learning, accreditation, industrial and academic leadership in several countries. Currently, he is a professor in the Department of Electrical and Computer Engineering at University of Sharjah. Previously, he is a professor and group head in EC department at University of Pretoria, South Africa. Prior to his appointment in UP, he was employed by the University of Queensland, Australia, University of South Pacific Fiji, BITS Planning, India, and the Civil Construction Wing, All India Radio. Professor Bansal has significant experience of collaborating with industry and government organizations. He has made significant contribution to the development and delivery of BS and ME programs for utilities. He has extensive experience in design and delivery of CPD programs for professional engineers. He has carried out research and consultancy and attracted significant funds from industry and government organizations. Professor Bansal has published over 300 journal articles, presented papers at conferences, books and book chapters. He has a Google citation, has over 10,000 and H-index of 44. PhDs, postdoctors. His diversified research interests are in the areas of renewable energy, which includes the wind, PV, DC, microgrid, and smart grids. Professor Bansal is an editor of several highly regarded journals like IET, RPG, IEEE Systems Journal. He is a fellow and chartered engineer IET UK, fellow of Institute of Engineers, and senior member of IEEE US. Thank you, sir. Thank you once again, and over to you, sir.
Okay, thank you very much for kind introduction, and thanks Professor Sarman for inviting me for this short-term program, and welcome all attendees. It is a great pleasure to present in this short-term program. So the theme of this course is renewable energy integration and smart grid. So I will give you an overview about the renewable energy integration and smart grid. I have already provided my slides to Professor Saravanan, so it will be shared to you. You have my contact details if anyone want to contact me later, so you are welcome to do that. So here what we are going to discuss is quite broad contents. I think I have the time about 2 hours for the presentation, and then we have some time for the questions and answers. So here we will discuss about the current trends for the power generation through distributed generation. I know in the morning Professor Dheeraj from IT Roorkee, he also covered. So I will briefly touch upon distributed generation, some DG interconnection requirements, and then what are the key renewable distributed generation technology, wind and photovoltaic systems. So we'll have brief discussion overview current status on this wind and photovoltaic technology. As we talk a lot about the renewables, to add more and more from the briefly see what are the main issues with the conventional power generation. And how we can improve the efficiency, reduce pollution from the conventional power plants. Then we briefly touch on microgrids and smart grids to conclude the presentation. So as we know that the current trend for the power generation is through renewable distributed generation. As we can see that how we had been generating electricity in past, and of course we are doing now as well through large generators, going for large size generators. But in recent time that approach is no longer economical because it involves large transmission and distributed generation losses. So the current approach for power generation is generation of electricity through renewable distributed generation close to the load centers. It has got several advantages, like in terms of that it will reduce the transmission and distribution losses significantly, and being the green technology, they offer positive impact on the environment. There can be several other technical benefits if these distributed generations are placed at appropriate locations. So you will find in the research large number of paper written on this, like location and sizing of distributed generation. So if these DGs are placed at appropriate locations in the appropriate sizing, they can offer several technical benefits in terms of improving of quality, etc. But with the distributed generation, there are several technical challenges. The technical challenges are in terms of, as we know, that these renewable distributed generation, these are highly fluctuating and intermittent in nature. For example, wind can fluctuate plus minus 25% within minutes. Same way, during night we don't have sunshine. Even during day, mowing clouds comes and there is no sunshine. So these renewables are fluctuating and intermittent in nature. Now we have the transmission networks which were designed maybe 50-70 years earlier, and they do not take into consideration of integration of renewable energy sources because at that time no one gave a thought that at some point of time renewables will be integrated. As we know that when we integrate DG, power flow becomes bidirectional. So the consumer of the electricity can also supply the excess power back into the grid through, for example, photovoltaic systems. When we have power flow bidirectional, so the existing protection scheme may not work well. We may require to have either completely new protection scheme or significant modification is required in the existing protection scheme. So this distributed generation, extremely important topic in recent time. Large number of research papers are being published continuously, and it will keep on doing that because this topic is really very relevant, and future is power generation through renewable distributed generation. So one of my PhD student who wrote this very nice review article on integrating renewable distributed generation, a review in IT renewable power generation in 2016. So very nice review paper. People who are working in this in the distributed generation, they can refer this paper, and several other students also wrote many other research paper in the area of renewable distributed generation. Now, when we integrate distributed generation to the grid, there are grid code requirements. IEEE has standard IEEE 1547. And several countries have developed their own grid code requirements as per the need for their countries. So in the left side, you can see some of the requirements for the DG integrations, like in terms of fault ride-through capability, voltage and frequency operating limits, active power control, reactive power control, requirement in terms of power quality, protection, etc. Just to demonstrate, for example, frequency and voltage control. So here you can see these two graphs. The upper one is the graph for and the so here frequency control for the Denmark case, the normal frequency operation is between 49 to 51 Hertz. If frequency deviates from this normal range, so we cannot have our operation for very long duration of time. Within the specified period of time, we have to bring the system back to the normal. So here, fast operation of control system is extremely important. If our control system is sluggish, so that can lead to have the unstable condition. Within the specified time, we have to bring the system back to the normal. We have to maintain the frequency of the system within the nominal range. Even you can see the below one, the case for China. So there you can see that normal operation bandwidth is very small. So here you will see the difference that any country designing their grid codes, so they can design their grid codes as per their requirements. Generally, we may think that when we are integrating these renewable energy sources, they will affect the power quality. But it may not be the case because it depends upon how the grid codes are designed and implemented. If we make our design code very tight, then many independent power system producers, IPPs, so they may not qualify for the bidding. So the grid code have extremely important in terms of maintaining the quality of the power system. Same way, the normal operation for the voltage control is between 1.1 to 9 per units. There are several grid code requirements. I'm not going into the detail of that. This topic itself is very wide, and you can refer more details about this. Now, let us talk about the main renewable distributed generations like the wind and photovoltaic systems. So first we talk about the very brief about the wind power system. Here you can see in this slide that by end of last year, worldwide, we had the wind installation capacity around 650 gigawatt. So this wind is extremely important renewable energy sources. If you see every year worldwide how much capacity is being added, so you can see approximately every year capacity addition is around 10%. In 2018 we had 591 gigawatt, then 10% of that around 60 gigawatt, so we reached around 650 gigawatt. So every year roughly the capacity addition is around 10% of its existing capacity. So the countries which are leaders in the power generation from wind are, of course, China, have the significant power generation from the wind, US, Germany, and our Indian system, they are also doing very great in power generation from wind. Then other countries like Spain, UK, France are also making good contribution. Now, what is the future trend that how much power install capacity from the wind we will have, say for example by 2050. So different models have been proposed by the researchers, like the advanced scenario, moderate scenario, etc. If you consider like advanced scenario, it means by 2050, after 30 years, we will have the installed capacity from the wind around 6,000 gigawatt. Currently we have worldwide installed capacity 650 gigawatt. So in next 30 years, our capacity from the wind can increase 10 times. If you consider some other models like the moderate model or some other models, in that case also we may reach the installed capacity from the wind between 3,000 to 4,000. It means the capacity we can have 6 to 8 times of the capacity what currently we have now. So wind will continuously being a good source of the power generation, and significant capacity addition will take place worldwide. So just to briefly show these main components of the horizontal axis wind turbine, which is the commonly used, commercially available wind turbine, horizontal axis wind turbine. Vertical axis wind turbine has not been so popular because of the several reasons. So here in the horizontal axis wind turbine, so this part what we call as the nacelle. So this nacelle will house, of course, the generator, and generally the wind turbine has the gearbox. Modern wind turbine, some of the modern wind turbine can avoid the use of gearbox because this gearbox is really problematic device, requires huge maintenance and adds significant weight as well. Then you have some other important like this different control system associated with wind systems, wind blades, and of course the tower of the wind turbine. These are the different components of the wind power system. Then you have this control like pitch control or some other associated control with the wind power systems. I'm not going into very much detail because we do not have the lot of time. Even I deliver the short-term program on the renewable energy, just covering this technology like wind, PV, photovoltaic system. It can take about 3 days course. So here just I am touching upon some key aspects of this wind system. If anyone would be interested in referring to this, so there is very good textbook by GM Masters, Renewable and Efficient Electric Power Systems, which very nicely explains the renewables like wind and photovoltaic system. Very well written for the as a good textbook, or it explains the concepts very nicely. So some of the slides you may find are directly taken from this book. Okay, so here as we know that the modern wind turbines will have either 2 blades design or 3 blades design. Okay, like in wind turbine which are being used for the power generation, they do not use multi blades. Also this Darius rotor is like the Sevenius type, so this is also not of the common use. And we also know that theoretical maximum efficiency what we can achieve from the wind turbine is limited by this Baird's limit, which is 59.3%. Okay, so if we see the rotor efficiency with respect of tip speed ratio, so this modern wind turbine will either be 2 blades wind turbine or 3 blades turbines. So both are commercially successful, and we may see both types of wind turbine, 2 blades and 3 blades. Okay. If you ask which one is best or which one is better, so both are successful. Everyone has got some pros and cons. So and none is like you can say all have the positive features. Both are commercially available. Different manufacturers, some manufacturers prefer to have these 2 blades, some manufacturers prefer to have 3 blades. If we see the efficiency curves for these 2 blades and 3 blades, so if we see for example 2 blades, in 2 blades the efficiency of the wind turbine can vary from say 40 to say 43%. For the 2 blades wind turbine, efficiency can vary from say 40 to 47%. So even this some variation from 40 to 47 or 40 to 43%, it can be a significant change. So if you see the optimum tip speed ratio, corresponding to optimum tip ratio, we can have the maximum efficiency from the wind turbine. So at what optimum tip speed ratio we operate the wind turbine is very important. You might be aware, so this is very common. when we talk about this wind power system, to explain the power curve or the associated wind speeds. So three wind speeds are there, which are very important to know. One is cut-in speed. If the speed is below cut-in speed, there is no power generation from wind. And of course, if speed is above cutout speed, or what we call as the furling speed, then also wind turbine is
I'm
stopped.
not able to see the.
Everyone is able to hear, please?
Sir, I'm not able to see the PPT.
What about the other participants, or anyone can see, please?
Yes, sir, we are able to see.
Yeah, so maybe individual participants, they may have your individual issues why you are not able to see, but I believe that most are able to see it. So please try to see what connections or what issues you have got.
Yes, sir, it's right.
So above cutout speed will stop the wind turbine, and there will be no power production, because maintaining the safety of the wind turbine is extremely important. So we do not want that to get our wind turbine damaged. So if the wind speed is above cutout speed, there will be no power generation. So when this wind speed starts increasing above cut-in speed, so you can see the power from the wind turbine will keep on increasing. As we reach the rated speed, the power will become corresponding to rated power. Even if the wind speed is increased further, we may produce more power, but we do not want to generate more power above the rated power, because it can affect the performance of the wind turbine. So there will be control mechanism which will keep the power from the wind turbine just fixed to rated one. Excess power will be just shaded. So excess power will be not generated from the wind turbine. So wind turbine will have the appropriate type of control which will avoid this excess power. So it can be suitable type of control, which can be pitch control, stall control. So that will be there to have the excess power being set. Now let us try to briefly understand about the generator technology, because we electrical engineer, for us it is very important to understand about the generator technology, associated power electronics. So if you see what is the generator technology which we have in the wind turbines. So basically these different generator technology we can classify as type 1, type 2, type 3, type 4 as per IEEE, or in Europe they can classify it as type A, type B, type C and type D. So what are these four different generator technology? The type 1 is induction generator. So it is basically induction machine of squirrel cage type. Then type 2 is slip ring induction machine, in which we can add external resistance. Type 3 is very popular type of generator technology, doubly fed induction generator, in which power can be extracted both from the rotor and stator. Then type 4 is your full scale generator which can use either synchronous generator or the induction generator. So here type 3 and type 4 are very popular generator technology which are commonly used in the wind turbine systems, in the modern wind turbine systems. So just to briefly explain about these 4 types of generator technology. Type 1, we have just squirrel cage type of induction generator. So here, as we know that induction machine draw the large current during starting. So there is some kind of starting arrangement, soft starter, to reduce the starting current. And of course, this induction generator requires the reactive power support. Okay, so this reactive power support is provided through external capacitor bank. So this generator mostly will be used like in the isolated application where there may not be grid supply. So this reactive power support will be provided by the external capacitor bank. So this type of generator you can find maybe small size generators being used in the remote applications. Then some improvement with respect of the type 2, we use the slip ring induction generator. In that, only the difference we see that in the rotor we can add the external resistance. By adding the external resistance, we can vary the slip, we can vary the speed of the induction generator. So basically, as compared to first type, in second type, we have more control associated with the slip. Slip we can vary up to 10% and so the speed. In the first one, the speed control or slip control is just 2 to 3%. Because here with the wind power system, we want to have the variable speed operation to extract the maximum power from the wind turbine. Now in type 3, which is doubly fed induction generator. So here you can see that it is of course slip ring induction machine operating in the generator mode. So here this type of generator will supply power both from the stator as well as from the rotor terminal. But we know that the frequency induced in the rotor circuit is function of slip, and the value of slip is very small. So the power from the rotor circuit we cannot directly use, because when we are feeding the power to the grid, it has to be the same frequency. Here the frequency what we may be getting in the rotor circuit, it can be 1 Hz or 2 Hz. Before this being fed into the grid, this frequency through the power electronic converters has to be brought to the rated 50 Hz frequency. Okay, so here the role of power electronic converters is extremely important, and here the power electronic converters rating will be around 30% rating of your induction generator. Then in type 4, type 4 generator, it can be based on induction or synchronous generator. It can avoid the use of gearbox as well, because we know that gearbox is really a problematic device. It contains a lot of weight and it requires regular maintenance. Huge maintenance, regular maintenance is required in the gearbox. Think of that different wind turbines at at a height, how this maintenance will be done. It is very challenging and very costly aspect. If the gearbox can be avoided, so it will be great relief for the wind industry. So modern wind turbines are being designed in which use of gearbox can be avoided. Here the power is being directly fed from the generator to the grid through the role of power electronic converters. Here the rating of power electronic converters is same rating as that of rating of the generator. Means the power electronic converters are 100% rating what we have the rating of the induction or synchronous generator. So this type of generator very popularly used is called as the permanent magnet synchronous generator. Now just to demonstrate some example, based on the generator technology. So this is an example of variable speed. So variable speed, it is type 2, which is a Vestas V80 wind turbine. So it stands for V80, means that the diameter of the wind turbine is 80 meters and its power rating is 1.8 megawatt, in which induction generator operate at the variable speed, and adjusting the rotor resistance, the torque speed curve can be changed and it can operate within the speed of 9 to 19 RPM. Then another examples of the doubly-fed induction generators, General Electric generators 1.5 megawatt and 3.6 megawatt. So this size of wind turbine very popular and will be commonly used in the wind farms, onshore wind farms. So this, as it states, that 1.5 megawatt wind turbines are like say best selling wind turbines in US in 2011. So now of course the technology is developing, maybe 3.6 megawatt wind turbine may be very popular. So with DFIG we have power generation both from the stator and rotor terminals. Then another example of General Electric 2.5 megawatt generator based on type 4. It is permanent magnet synchronous generator, PMSG. So here type 4, it has the converter rating, same rating as that of your generator, which is based upon the type 4 type of generator. So as I mentioned that in wind system we are interested in the variable speed operation, which way it is advantageous, which way it can produce more power. Okay. So as we have seen the variation of the wind and the efficiency, what we call as the coefficient of performance. So here these two slides shown, one is Vestas manufacturer V82-1.85, means that it is Vestas 82 meter wind turbine with the power rating of 1.85 megawatt, and it is a squirrel case induction generator. The another example is General Electric 2.5 megawatt with rotor wind turbine rotor diameter as 1.03 or 8 meter, and it is permanent magnet synchronous generator. So obviously the right side slide is like the modern type 4 generator, whereas this left side it is a all type of generator based on type 1. Okay, so we'll see which way it is different. If you see the power curve of both these is quite similar, but the coefficient of performance, how the efficiency will be varying of these two types of generator. One is almost fixed speed squirrel cage induction generator, another is variable speed generator based on the permanent magnet synchronous. So how their coefficient of performance characteristic is there. Here on left side, if you see the coefficient of performance efficiency, you will see that if the wind speed varies, for example 5 to 10 meters, okay, if the wind speed is say 5 meters, you can see the value of Cp, it becomes 0.2. If the wind speed is around 7 meters per second, the value of Cp is 0.5, around 0.5. But as even speed increases, the value of Cp goes very down. Okay, so we know the power from the wind turbine is half rho AV cube multiplied by Cp. So with the variation in the wind, Cp varies significantly. But here in the other type of generator, which is variable speed, normally the wind turbine where you install this generator, the speed will be generally in say range of 5 to 10. So here you can say when the wind turbine varies say from 5 to 10, the value of Cp is quite flat, is almost not much variation. So between 5 to 10, the value of Cp will be just from say 0.41, it can go to 0.42. So means that even with the significant wind speed variation, the power from the wind turbine is quite consistent, constant, and quite high. So you can see that basically that's why in the wind turbine, modern wind turbines, we will be using the variable wind speed system so that we can extract continuously more power from the wind turbine. I already explained the issues with respect of gearbox. Gearbox will add significant weight to the nacelle. Gearbox requires regular maintenance. The oil required to be changed, and it can be the common cause of the failure. Some wind turbines are now getting rid of this gearbox. Like for example, the manufacturer Enercon is a leader in this area, so they are using the direct drives, avoiding the use of the gearbox. Okay, So here you can see some of the wind turbines from the different manufacturers like this: Mitsubishi, Siemens, General Electric, Vestas, of the different wind turbines: 1 megawatt, 2.3 megawatt, 3.6 megawatt, and 7 megawatt, 8 megawatt. So which appears to be the largest size of wind turbine. And here we know that in wind power system, how the power is produced, how much power we can extract from the wind turbine. What is the governing equation for that? So power available in the wind is given by equation half rho A V Q. Now on which factor it depends? Of course, area A is the area of plates, V is the wind velocity. So power will vary cube of the wind velocity. So we would like to obviously place the wind turbines, wind farms in very good windy side, so we can extract more power from the wind farms. Power will change cube of the wind velocity. So slight bit variation in the wind, slight bit increase in the wind, power increase will be significant because power increase will be cube of the wind velocity. Okay. Then another factor is the area of the blades. Area we know is pi by 4 d square. So power produced from the wind turbine will vary square of the diameter. If the diameter we increase, power will increase square of that. For example, if the diameter of wind turbine is 10 meter, power produced is say square of 10, that is 100 units. But if the diameter is increased to 20 meters, power produced will be square of 20 is 400. So power produced changes from 100 units to 400 units, 4 times. The diameter increase is just double from 10 to 20. Of course, when we increase the diameter, cost will also increase for the wind turbine. The cost increase is somewhat just double, but power increase will be 4 times. So that explains the economy associated with the wind turbine to go for higher and higher size of the wind turbine, larger size of wind turbine, because we can extract more power from the wind turbine. This slide very interesting, and you may see this in several research papers as well. This slide explains the development in the wind turbine technology, increase in the size of the wind turbine systems, development in the generator technology, and its associated power electronics. So how the development in the wind turbine rating has taken place. Around 1980s, the largest size of wind turbine was around 50 kilowatt with rotor diameter around 15 meter. The generator technology what we use is basically squirrel cage induction generator, or slightly later stage we started using the slip ring induction generator. So basically generator technology was type 1 and type 2 generator technology. So here the role of power electronics was minimum even up to 1995. The role of power electronics was minimum. We can add the external resistance in the rotor circuit, can increase slight bit slip or speed. The role of power electronics was minimum. But around 2000, we had the generator technology, which was doubly fed induction generator, in which the role of power electronics is around 30%, and we increased the generator rating around 2 megawatt with rotor diameter around 80 meter. And then of course after that we are having the wind turbine 8 megawatt, 10 megawatt can go wind turbine diameter of 190 meter using the generator technology, very popular generator technology, permanent magnet synchronous generator. So you can see the role of power electronics is extremely important in development of the wind turbine technology. Okay, so this is like very recent slide. You may be interested what is the largest size of wind turbine. So you can see that Siemens has recently unveiled 14 megawatt of wind turbine synchronous generator of the rotor diameter 220 meters, and it is of course a offshore wind turbine which is the largest size of wind turbine in the world. Even this wind turbine rating can be boosted to 15 megawatt. So one wind turbine can supply power to average 18,000 households in the Europe, and 30 wind turbines can supply power to a city in Spain. And Siemens is contributing a lot in the wind power generation, has already installed over 100 gigawatt both for the onshore and offshore wind turbines, and which has helped to reduce the emission significantly. Now I'll just give you one example, a practical example of the wind farm. I worked in Fiji Island during 2006 to 2008. At that time, a small wind turbine, for them you can say is quite significant capacity, around 10 megawatt. So in the behind you can see that different wind turbines. My picture is in the center. So we had been visiting, doing some consultancy for this wind power plant. So they installed a 10 megawatt wind farm. In the behind you can see the wind turbines. So this way basically 37 wind turbines were installed. You can see the pictures of few wind turbines. So you can see these wind turbines are 2 blade wind turbines. And just to give you some technical information, this wind farms, very small wind farm, because Fiji is a small island country, population is just like 1 million, so power requirement is not that huge. So for them it is significant capacity. So the installed capacity 10 megawatt, total 37 wind turbines. Each wind turbine is 275 kilowatt. Is some Bvritn French make wind turbine. Cut-in speed 3.5, rated speed 13 meters per second, furling speed 25 meters per second, hub height 35 meter, blade diameter 32, and you have seen that number of blades are 2. Approximate distance between the two adjacent wind turbine 100 meter, because you have to keep the suitable distance between the adjacent wind turbines. We do not want the wind turbines to be too close or too far away. If these are too close, then the power produced from the wind turbine will be affected. If they are too far away, it means that area of the wind farm is not properly utilized. So this requires a area of around 7 kilometer. Then slide with more information, which type of generator. So it is like the induction generator in which you can change speed, the slide bit. So it is basically called as the pole changing generator. You can change the pole of the generator from 4 to 6 or 6 to 4. You can have slight bit variation by changing the pole, and how much power you can extract. If it is low speed, then power produced will be around 70 kilowatt. But if it is the rated corresponding rated, it can obviously generate its rated power. Type of control is pitch control, and it is like the induction generator squirrel case. Obviously it needs the reactive power support through capacitor banks. So each wind turbine will get the reactive power support for 170 kVA from the capacitor banks. And these wind turbines are comprised of the fiberglass, and it gives you some the annual energy output from the wind farm 11.1 gigawatt hour. How much is the investment in the project? Around 28 millions, or the actual cost is 34 millions. Payback period, so it can recover the cost in 15 years, and the life of plant is around 25 years. Power will be generated by the generator at the voltage level of 415 volts, which will be stepped to 33 kilowatts by means of a transformer. So means that it is wind farm will be connected to the grid at the voltage of 33 kilowatts. Okay. Then the another wind turbine technology, offshore wind farm. So it is upcoming technology. Current installed capacity is around 30 gigawatt. Mostly installation is in the Europe, and Europe is keeping some big target to have 150 gigawatt by 2030. Some other countries are also exploring the power generation from the offshore wind farm, because this is also very important technology. You may find in recent times some research papers coming out based on the offshore wind farm. Okay, so what kind of technology currently we have for the offshore wind farm? Basically, these wind turbines will be installed inside the sea. Now, how much depth we can go inside the sea? So we can, current technology we may have that we can go in the depth around 50 meters inside the sea. But in coming time, we can go more deep into the sea, because we have more wind velocity available as we go deep into the sea. And of course it will require more cost for the structure tower, but having the more wind velocity will be beneficial for generating more power. Whatever we have seen, the large size wind turbine like the 7 megawatt or even higher, so this will be mainly used in the offshore wind farm. Okay, then the another wind turbine technology. In fact, recently I examined one PhD thesis from the one Victoria University in Australia. So you can see a small size of wind turbine, 3 kilowatt wind turbine installed on the rooftop of the building at Victoria University. The student did some research work for the small size wind turbine in Australia and in India for the Tamil Nadu state. We know that for the photovoltaic system, small scale is very common. Like these PV systems can be installed on the rooftops for the individual consumers or some commercial building, university buildings, which is very common. But we have not seen the much development around small size wind turbine. Here this is an example of vertical axis wind turbine. The installation is not that user friendly, not that easy as we have for the PV system, and of course it will cause forces on the rooftop as well. But this can be very popular in coming time, and if this technology becomes very much commercially successful, then we can see in future there might be large number of installations based on the small scale wind systems. And wherever the place we see is good windy areas, large number of wind turbines can be installed in future on the rooftops of the different buildings. Having briefly talked about wind systems, now we will talk the another very important and very great technology, that is photovoltaic systems. So here with these photovoltaic systems, you can see that Earth's surface receives the huge sunshine from solar, and it receives the power of the order of like 1.2 into 10 raised to power 8 gigawatt. If the whole power we can tap from sun just like 1 hour, so it will be sufficient to satisfy the demand for the whole universe for 1 year. So it means that we have huge potential from the sun. If we can significantly tap the power from the sun, then we may not require some other resources for power generation, fossil fuel or some other sources. And this PV system technology is direct conversion of sunlight into electricity. It is very much environment friendly, very much reliable, involves no moving part, complete silent operation, requires very low operation and maintenance cost, and very important aspect that the PV systems can be installed very quickly if you compare with respect of other power generation like hydro or coal based. So their gestation time could be 7-8 years. The large size photovoltaic system can be installed in a time of 1 year, whereas the coal based or hydro based power system may require 7 years or 8 years to complete the project. This PV system has the installed capacity just reaching what we have the wind. You will see in the coming slides. So the current installed capacity is around 650 gigawatt, and the capacity will increase at very fast rate. Now, what the options we have for the photovoltaic systems, where this PV system can be connected, installed. So we can have like the obviously grid connected PV systems, which can be mounted on the rooftop of the buildings. In some of the building, it can be integral part of the building called as the BIP, building integrated photovoltaic systems, or the large size plants. They can be obviously placed on the ground. Of course, some metal structure is there. They can just install on the metal structure placed on the ground. Then we can have this.
Sir, sorry
Yes,
for the
please.
disturbance. If you want to take 5 minutes break, take some tea, something. If you want.
Yes, okay, okay. We'll just have the 5 minutes break, please.
Yes, yes, sir.
We'll continue.
Because it's 1 hour, it's over. To take some tea, snacks means somewhat you are also somewhat energy.
Okay, no problem. We'll just stop for 5 minutes.
Okay, okay, sure.
Thank you much. But we will just leave it like that and we'll start in 5 minutes.
Sure, sure, sir. Dear participants, it's a 5 minutes break. It will start 2:40.
We can continue, please.
Sir, yes, sir, you will continue, sir. So welcome back to our session.
Okay, thank you very much. Participants, we are discussing about the photovoltaic systems, different configurations, options. As I mentioned, many of these slides I am covering from the book GM Masters, Renewable and Efficient Electric Power System. This is like the excellent book even to adopt as the textbook, which very nicely explain the wind photovoltaic systems, other renewable energy technology, gives large number of the examples. So through which students can easily learn. So other options, we have the photovoltaic systems, which be like a standalone system. So in the standalone system, not connected with the grid, we have to see what sort of backup we have. So backup would be in terms of like batteries, and then diesel generator may be an additional option. Then if we talk about the photovoltaic systems that can be used for the irrigation purpose, water pumping applications. So in that case, we want to design the PV system with minimum cost. So that PV system will not be having any battery storage system, because that increases the cost. And when we are using for the irrigation purpose, water pumping application, whenever there is sunshine, we can just use for the irrigation purpose. It not associated with the particular time. Okay, so that will now make the system less costly. So here you can see the standalone systems, PV system directly connected to the load, water pumping system. Now in the photovoltaic system, we have the IV characteristic that we call as the current versus voltage characteristic of the PV system. We call this IV curve of the PV system. And we have got the different components of the PV systems, like the load, can be batteries. So understanding their characteristic is very important. For example, whatever the load we have, it will have its own IV characteristics. The load can be your resistive load, or the load can be a motor load. So what is the IV characteristic of the load? And where this IV characteristic of the load will cut the IV characteristic of the PV system. So where these two curves meet, that will be the operating point of the system. Our objective is to operate this system corresponding to this neck point. This point we call as the MPP point, maximum power point for the system. So if we have, for example, resistive load, whatever the value of resistance we may have, if the resistance we can vary, so we can have the different characteristics for the resistive load. Okay. Our objective is to have the resistive load characteristics corresponding to this MPP point, corresponding to neck point. Corresponding to this, PV system will transfer maximum power to the load. Okay. So through potentiometer, if we can have the resistance corresponding to this neck point, it will transfer the maximum power to the load. So from here we can develop the concept of MPP-T. As we will see that we don't have like this one operating curve for the PV system, but during the day the sunshine keeps on changing. So you'll see that we'll have the several IV characteristics of the PV system. Even if we adjust the MPP corresponding to a neck point, but it will not be the peak point with the varying sunshines. So it will be operating these points, but the peak points will be these points, so which are quite far away. So it means that we need a device called as the MPP, which can operate the system corresponding to MPPT condition, and the device which does so is called as the MPPT device. So the role of MPP device becomes extremely important in photovoltaic system. We saw this similar thing in wind system as well. So in wind system, our objective was to operate the TSR, tip speed ratio, corresponding to optimal point. Similar way here also our objective is to operate corresponding to MPPT conditions. Some other types of loads, for example DC motor, which is used in the water pumping application. Here, as you know, that DC motor will require slight bit large current during the starting. Once the motor is started, its current will reduce. So here DC motor characteristic, if we superimpose on the characteristics of the PV characteristics, so here in the morning, say around 10 a.m. when there is good sunshine, then only DC motor will start. But if we can have some mechanism or some device which can help in starting of the induction motor corresponding to low insolation, say 8 a.m. in the morning. Once the DC motor can be started, then it will keep on running for the longer duration of time. So the device which can help is called as the linear current booster. So this linear current booster can act like the MPPT. So here the LCB, if installed with the DC motor, it can increase the operation, say for example 2 more hours. So it can supply water for 2 more hours in a day. So this way this device can help in getting more power output from the DC motor, or it can PV system can supply more power. Then of course in the PV system we can have other devices like the battery storage system. So battery storage system will have their own IV characteristics. So we need to have the understanding the IV characteristics of the battery systems. So during charging and discharging, they will have slightly different characteristics. Of course, the characteristics of these batteries IV characteristics are quite straight line. During charging and discharging, they are slightly tilted in the different directions. Then the concept of MPPT I explained. I'm not going into too much of detail because of the time constraint. But here a MPPT can be for example, a buck and boost type of converter. It will have this like an inductor, capacitors, a diode, and a switch. Same, this converter being applied to a DC motor. So here this switch is not like the normal switch, but it is a transistor switch which flip-flops at high frequency around 20 kilohertz. So during one cycle, the inductor will store energy then next instant the energy stored will be dissipated to the capacitor. So energy stored keeps on fluctuating between the inductors and capacitor. So here, how much time we can keep the switch on and off in one cycle, that we call as the duty cycle. So by changing the duty cycle of the switch, like how much in one cycle, how much duration this switch keeps on and how much duration this switch is in the off position, that we call as the duty cycle. So by changing the duty cycle, here in this figure you can see that duty cycle just like 0.5, it means half of the time the switch is off, half of the time the switch is on. The duty cycle can be less than 0.5, it means that less than 0.5 time the switch is on and more time it is off. Or D can be greater than 0.5, it means the switch on time is more, off time is less. So by changing the duty cycle, we can see that whether we will get the more output, more output, more voltage at the load or less voltage at the load. So we can vary the voltage across the load just simply changing the duty cycle. So this is the governing equation, that how much output we'll have with respect of the input from the PV system. It will be simply decided based on the duty cycle. By changing simply the duty cycle, we can change the output voltage. Now I will explain the concept of DC and AC rated power. You know that PV system, it generates DC power. So we may specify that the power rating of the PV system is, say, for example, 1 kilowatt. Now this rating is DC or AC. Understanding is very important. So we have to estimate the performance of PV system, that rated DC output of an individual module under some standard test condition. And the standard, like if you want to compare the performance of PV systems, so you have to compare with respect of some standard conditions. So the standard conditions are like the standard test conditions, which are like, say, one sun, air mass ratio of 1.5, the shell temperature of 25 degree. So the sum of these conditions we compare. Now the AC power output from the PV system will be defined as DC power output from the PV systems under standard test condition multiplied by conversion efficiency. So this conversion efficiency, it is not only the efficiency of the inverter, but it accounts for the efficiency lost because of the dust accumulated on the collector plates, mismatching of the modules, and difference in the ambient conditions. So if all these factors are combined, so the conversion efficiency or the losses in the system, it can be in the range of 20 to 40%. Just to explain what is the meaning of mismatching of the module. For example, we have these two modules, maybe from the different manufacturer. Initially you installed PV system, you had one particular manufacturer. Later you want to add some more PV panels, but it is not completely matching. Means that you have the module, initially you had the module, its power rating was 180 watt, and this 180 was at 30 volts and 6 amps. But later you added the PU module which also have the power rating 180 watt, but this 180 watt is now being supplied through 5 amps and 42 volts. Okay. If these two modules are combined, so we may expect that total power output we may get 180 plus 180, 360. But practically what we will achieve, it will not be 380, but it will be less. How much less? It will be 330 watt. Why 330 watt? Because of course if we connect these two modules in parallel, current from one panel is 5 amps, current for another panel is 6 amps. So in parallel circuit, the total current becomes 11 amps. But the voltage rating of one module is 30 volts. The voltage rating of another module is 42. So in parallel circuit, we have the same voltage. So the voltage which is lesser one, that will be the voltage across both the modules. So we have basically 11 amps and 30 volts. So which will give us 330 watts instead of 360 watts. So basically because of this mismatch of the modules, means that power rating can be same but current and voltage rating are different. So the power rating what you get combined will be reduced. So this is called as the mismatch. So because of mismatch, efficiency loss can be of the order of 3 to 4%. Now, if you would like to decide the system sizing, for example, you want to decide your PU systems, which first we consider the case that it is connected with the grid. So you want to use for the some commercial application. You want to sell the electricity to the grid. So how will decide the system sizing for the grid connected PV system? Okay, so you want to decide, so you need to do some calculations. For example, first you have to see that you want to install PV systems where you are going to install in the rooftops. How much is the area available on the rooftop? How much PV modules you can install? And then, of course, if you have sufficient space, then you will also be interested in knowing that the utility is interested in buying of how much electricity, means that how much kilowatt hour per year they are willing to buy. Okay, so from that information you will decide that that this much of energy you are supplying. So to supply that much of energy, how much DCP power output is required and how many modules will be required. So accordingly you can decide the system sizing of the grid connected system. But of course, when you are practically designing, so in addition to that, you may also give the consideration that what are the different components like the PV modules, inverters, batteries, etc. are commercially available in the market. Okay, when we have to decide the system sizing of standalone system, we saw that deciding the sizing of the grid connected system is more around non-technical parameters, like how much space is available, how much energy utility is willing to buy. But here, when we are deciding the system sizing for the standalone system, so here it is more around the technical parameters, requirement of the people. When we have standalone system, then we have to give consideration to a backup system. What kind of backup is going to be there? Batteries, storage system is there, whether we have diesel generator or not. And then we have to decide how much load needs to be supplied. Okay. So if we are installing the photovoltaic systems, it can be used for the residential purpose, or it can be maybe some other applications. So we have to decide how much will be the load. So we have to make the estimation for the load. If you're talking about the household, we may see that what are the different types of loads, your lighting loads, fan loads, if you have refrigerator, TV, electric on, microwave, so all the different types of load, we are just going to make an estimate. Then we will see what is the direct effect of the load. Based on that, we will have the estimation of the load, and that will help in deciding the sizing of the PV systems. And then of course we have to make a decision that how much load we want to connect at a time on the PV system. And you can see that the load will be comprising of your static load like this lighting load, and then part of the load can be your motor loads. So for system sizing, we make an estimate of the load that needs to be served by the PV systems. We have to make a trade-off between, like, whether we want to make system more expensive, we can supply a lot of load, or we want to have these basic systems in which minimum load will be supplied through these PV systems and battery systems. Can we have the options that we can have more DC loads, which can avoid unnecessarily efficiency lost in the inverters? So what fraction of the full load should be the backup generator? If you have motor loads, in motor load in the starting there will be large currents, so we have to give consideration for that as well. Because of time constraints, I am not going into very detail of the discussion, but just I am trying to focus on key points. Then in PV systems we have these batteries. So the role of batteries is extremely important in the renewables, in the electric vehicles, even in the large scale power generation. The role of batteries is extremely important. A battery is the future technology. So with the batteries, there are a lot of technical, non-technical factors associated in deciding the suitable type of batteries. So batteries will provide the storage, and there is like lot of interest in the battery technology in renewables, hybrid electric vehicles. There are different types of batteries options available. Which one can be best for a particular situations? So we may need to consider several technical, non-technical parameters in terms of cost, weight of the batteries, number and depth of the discharging, charging, efficiency, etc. So we may need to have comparison of the different options that we have available with the batteries and their technical requirements, like the lead acid batteries, lithium ion, etc. What are their power density, how much is the cost, how much is the cycles of charging, discharging, how much time it takes in the charging, because that can be very important factor, the charging time in the electric vehicle applications. So we have to give the consideration of lot of technical, non-technical parameters to find a suitable battery technology, battery options. Okay. So some status for the photovoltaic systems, what we have the worldwide installed capacity from the photovoltaic systems. Currently installed capacity, we are reaching around 750 gigawatt at the end of this year. Then you can see how much capacity is being added every year. We show in wind that capacity addition worldwide every year is around 10%. But here in the photovoltaic system, capacity addition every year is around 30%. So in about 3 years time, worldwide installed capacity will just become double. So PV technology is growing very fast. Lot of capacity addition is taking place from the PV systems. The countries which are leader in the PV installations are of course China, US, Japan, Germany, and our Indian system is really doing the great in the capacity addition from the photovoltaic systems. This is the like this the PV plants worldwide. This slide I prepared few years ago, but the PV technology is changing very fast, and you can see that in recent 2-3 years several big PV plants have come, like in Egypt 1.8 gigawatt under construction. China has a 1540 megawatt power plant, and there are several other large scale photovoltaic system. In our Indian power system, photovoltaic system, last year we completed Bvritn solar park in Karnataka, spreading over 53 square kilometer with the solar park capacity of over 2000 megawatt. That was at that time largest PV system. But that is not only the plant. In Rajasthan we completed 2245 megawatt PV plant, and more important, we know NTPC, which is the National Thermal Power Corporation, public company, Bvritn, which has the power operation in the coal-based and gas-based power plants, but recently entered in the renewables business. NTPC plans to add 32 gigawatt in the next 10 years. So they want to have their energy mix from 96% currently to 70%. So they want to invest significantly in the renewables. So this PV system installed at the University of Queensland. Previously, I worked at University of Queensland, Australia. At that time, we used to have around 1.2 megawatt, but now the PV system capacity gone more than 5 megawatt. The PV system installed on the rooftops of the building, different buildings in different campus. So total capacity over 5 megawatt. Through this website, in real-time system, today or tomorrow, you can see that during the day how this power generation is taking place, and you can, through visiting through this website, you can find several interesting information related to the practical power systems, which type of PV modules, inverters, whether it is single axis tracking, double axis tracking, battery storage system is not there or not. You can find several interesting information. Okay. Now, one question will come to our mind, that if we have the PV system which is connected with the grid, whether we should have battery storage system or not, which way it can be helpful. Just to explain the University of Queensland case, we have PV system connected with the grid, and they have battery storage system, which is not like the full size, but this battery storage system can help the utility in managing their load demand. So if the battery storage system is there, that can help the utility in meeting their peak power requirement. So whatever the energy stored in the batteries, so that can help during the peak demand of the system. We have talked about the wind photovoltaic system. Now I just want to give the some idea about the conventional power generation, fossil fuel power generation, coal-based power generation. This slide you can see that large number of countries, big countries like US, China, India, so they have significant power generation from coal-based power plant. Other fossil fuel gas also there, and so several countries producing significant power from the coal-based power plant. So the major issue with the power generation from the coal-based fossil power plants is the emission, CO2 issue, and this is the major issue worldwide, that huge emission is produced. That's why we are moving towards the renewables. If we see the situation for our country, like what is the energy mix we have, we can see how much we are producing in India from the non-renewables, coal. So with the coal we are producing more than 53.5%, then gas 6%, around 6 or 7%, nuclear around 7%. So total non-renewables, coal plus gas plus nuclear, it is around 62.5%. Then from the renewables, wind we have share around 10%, solar we have share around 9%. Then of course we have bio around 3%, large hydro around 13%. So total we have 37.5% from the renewables. So our Indian power system installed capacity 370 gigawatt currently. 230 is from non-renewables and 128 is from the renewables. So still we have to increase more and more share from the renewables, because still more than 50% coming from the coal, which is really a big issue. This article published in IEEE Spectrum this year. So what are the plans for our government? Government plans to boost renewable energy 175 gigawatt by just like within 2 years, and then increase it further by 450 gigawatt by in the next 10 years. So our government has great plans to add more and more power generation from renewables. Sometimes we think that government plans are slow, do not complete in time, but in renewables, whatever the plans we made for the renewables, like for example PV system, we achieved before time. So we should be really proud of that. And in fact, whatever we used to listen in the past, that we always have the shortage of the generation, we always have the gap of the generation and demand of the order of 10 to 15%. But now there is as such no shortage. Our generation and demand are quite matching. So there is no more power shortage issue. Only the things we have to consider to move away in plant matter from the conventional to renewable generation. So this slide you can see very interesting how the energy mix is there worldwide between say 2000 moving forward to year 2040. So if we see around 2000 or even up to 2010, this black one is obviously the coal, then the second one is hydro and nuclear, then below one is the gas power generation, and the lowest graph is for the renewables. So we are picking up from the renewables. We are trying to reduce power generation worldwide from the coal. And if you see what we are now, still worldwide, huge power is being produced from the coal, and if you add gas, it is significant. So we expect that say next 20 years, we may have this, highest power from the renewables. It will take more next 20 years, and we have to generate power from the coals maybe next 50 years or so. So what are the issues with respect of power generation from coal? You can see the efficiency of coal-based power plant is quite low. Of course, efficiency of renewables can also be low. For example, PV system efficiency is very low. Low efficiency is concerned, but not that great, because anyway, sunshine is free. So we are not burning the fuel. But here in coal, we are burning coal. It's like the burning of money, and then a lot of pollution as well. So efficiency is a great concern. If you see worldwide, efficiency can vary, say around 30%, and can go up to 43%. Even slight bit increase in the efficiency can have big impact, because we have more than 200 gigawatt power generation from coal. So increasing the efficiency is really very important. One of my PhD students did research how to improve the efficiency of coal-based power plant, how to minimize the pollution from the coal-based power plant. Because of time constraint, I cannot go into the detail, but you'll see in power plant when we are producing the steam in the boiler, basically during the process what we call a layer will be deposited on the water walls where the steam production will take place. You can see this layer that we call as the slagging thickness. This thickness will badly affect the heat conductivity. If this thickness is very high, the conductivity will be badly affected. So what we can do, if we can make use of all the recent modern intelligent technologies, if we can integrate real-time simulation with online learning technology to improve the combustion process of the boiler, it will reduce the emission, it will increase the efficiency. Because as I mentioned, for the next 50-70 years, still we have to produce power from the coal-based power plant. We don't have any option. So the only thing we can do, increase the share of renewables as much as we can, that we are doing. But whatever we have the coal base, so we increase the efficiency, reduce the emission. So this work was later published in this book. So we developed some grid, some source code like in Corba, MATLAB, Simulink, Console, etc. And these codes are freely available. So this research is not only applicable for the coal-based power plant, but wherever we have the boiler, like in the paper industry, steel industry, this can be applied. Okay, now to touch on microgrids, hybrid power system, we still have the community which do not have access to the grid. It can be due to the remoteness or some other reasons. The grid supply may not be feasible. So how the electricity is supplied to those community is mainly through diesel. And electricity generated from diesel is extremely costly because of the cost of fuel, transportation cost, operation and maintenance cost. If we can integrate renewable energy sources which may be available to those locations, wind, PV, bio, whatever the renewables options we have, integrate with the diesel to make a grid called as the hybrid power system. So the cost of the system can be brought down and the quality of life of the people in the remote areas, it can be improved. So the hybrid power system is extremely important to meet the power requirement for the remote companies. Okay, this slide, my apology that you may not be able to see, but this is taken from the paper Electric Power Components and System published in 2015. It gives you very nice comparison of the different renewables. What are the present status? What are the research challenges and opportunities? What is the trend? Okay, we discuss like this wind onshore, wind offshore photovoltaic systems. Then there are some other technologies which have not been so successful at the commercial level. Of course, battery is really doing great and a lot of scope is there for the improvement in the battery technology. Present status we have talked. Then like say in wind, what are the research challenges are in terms of reliability, interconnection issues, grid code compliance, develop the converters for higher voltage like 3.3 kV, development of converters based on the new semiconductor devices. Then in offshore, basically issues are around maintenance. The cost of the offshore wind farm will come down as we have more and more capacity addition. Same is the case for PV system, cost will come down as we have more and more capacity addition. The opportunities or challenges are around development of the inverters for the higher voltage. So this is very interesting comparison. I'm not going into the detail. And then we are ending out of time, but to briefly touch upon Give me please few more minutes. Smart grid. So what is this smart grid? The smart grid is not a complete replacement of the existing grid. Because if you think that, okay, we'll completely close down the coal-based power plant, then situation will become very complicated. People will be there without electricity. That we cannot call as a smart grid. So smart grid is not a complete replacement of the existing grid, but to complement it with the features like we need to have centralized generation, then adding more and more from the renewable distributed generation, integrate as much as we can do from the renewables. Electric vehicles are likely to come. Delhi government already announced its plan. Storage system role is extremely important. Phasor measurement units, smart metering, they are going to be the integral part of the smart grid. How we can make use of IT to optimize the capital assets, reduce operation and maintenance cost. Then if you compare smart grid with respect of traditional grid, so in smart grid, in addition to centralized, we have this renewables, distributed generation, integrating renewables, electric vehicles are likely to come. Obviously, power flow becomes bidirectional. There is two-way communication. The metering is very important, so we need to have the digital metering. The smart grid should have the features like self-monitoring and self-healing. And customer have got several choice. There is no more monopoly in the power system. What are the subsystems of the smart grid? 3 subsystems like infrastructure, management and protection. Here infrastructure we have the generation, transmission and distribution. Of course, in addition to conventional, we have the generation from the renewables, electric vehicle to the grid or grid to electric vehicle, then smart information systems in terms of phasor measurement units, smart communication systems like fiber optic communications, then smart management, how we manage our grid, how we manage the demand profile, how we reduce the energy loss, how we minimize the emission, what are the tools and techniques, programming we use, like the machine learning, game theory, etc., and how we protect our grid. So reliability and protection of grid is extremely important. Protection of microgrid is extremely important. In the smart grid, the utility will get a lot of data from the consumers. So maintaining the security and privacy is extremely important. So some of my publications, books, in which of course several my research students, PhD students, postdocs, and other researchers through collaboration contributed a lot. So we published some books, like one book dealing with the power system protection in the smart grid environment. So this can offer a good book, maybe undergraduate and postgraduate level, dealing with the power system protection aspects, covering some modern topics. Then contributed some book on the distributed generation, renewable energy. Recently published book on power electronics drives, advanced applications. So this can offer a good textbook at undergraduate or postgraduate level. So without taking much time, I would like to thank you, all the participants. I hope you enjoyed my presentation. It was knowledgeable, and I would like to convey my best wishes for all organizers, and I'm happy to take some questions. I just stop, but I'm happy to take them. Thank you very much. Thank you, everyone.
Thank you, sir. Professor Ramesh Bansal, sir. It's a very excellent presentation. I hope all the participants are enjoyed your session for the renewable energy and the integration and smart grid. Mr. Sainath, sir.
Sir, same sir.
You to say what of thanks to our resource person. After them, if the participant interested, we interact with the resource person.
Okay, sir.
Okay.
Okay, sir. With your permission, sir.
Okay, thank you,
sir. It's a very great session, sir. And once again, I'm very thankful for you, sir. Especially the topics called current trends, grid integration scenarios of wind and PV systems. A very brief insight in all these things. Cultivated the research culture among us, and this today's session has triggered many research problems, and we are all very honored for you, sir, for having a session. And once again, I'm very thankful for you for immediately accepting your invitation in spite of many works and giving us time for us, and very thankful for you, sir. And also we are also waiting for your future webinars also, sir. Thank you a lot, sir.
Yeah, so thank you, Naresh Kumar, and thank you, Professor Saravanan. So in fact, it is a great pleasure for me to encourage the young participants, researchers doing the research, and encourage those through these webinars, seminars, interact with the young researchers, postdocs, PhDs, faculty members, wherever we can contribute. So I'm happy to take questions from the participants, organizers, faculty members, students. Please feel free to ask any questions you may have.
Dear participants, please unmute your video and directly interact with our resource persons. It's a very great chance to interact with our resource persons.
So feel free to ask any questions.
Good evening, sir.
Good evening.
Good evening,
please,
sir.
When you speak, please mention your name and your college or the area in which you are working, just to introduce slight bit.
Yeah, sir. Very good evening, sir. Myself, my name is Sainath Singh. I'm working in the Bvritn college only. Sir, I'm having a doubt. That is, for a grid-connected PV system, how far these battery storage systems are feasible? If you have connected a battery for a grid-connected PV systems, is it feasible? Well, is it reliable, or it will be commercially success in that area? Can you give us any brief insight regarding this, sir?
Yes, so this is a really very good questions, and in fact I try to briefly explain as well. Whenever we are adding batteries, of course it will make the system more costly. But we have to see like what is our need, why the battery is required. Is the grid completely reliable? If grid power fails, so partially we can supply the load. Even, for example, this solar system, its capacity is significant, and it is helping the utility. We are supplying power to the utility, and utility has supported our project. So if we have the battery storage system, it can help the utility in maintaining their demand profile during midday, when the during the time, say in the evening, when the load is maximum, the power from the PV is reducing, but still, if there is storage system that can help in managing the peak demand of the system. So of course, when we are adding the batteries, it will increase the cost, but it can help on several technical aspects, managing the demand profile, even can act as a backup when the grid is not very reliable. I hope my answer is fine.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Good, sir.
Any other participants? Unmute your audio.
నేను సాయి ఇద్దరు ముగ్గురు సార్ సాయి సాయి ఎందుకు వాసన
Sir, good afternoon, sir.
Good afternoon, please.
Myself, I'm Gandhi from Nanamani Engineering College, Namakkal, Tamil Nadu, sir. I'm having one doubt regarding the energy storage device. Currently, we are using lithium and lithium ferrophosphate. So, what about the future of the energy storage device, sir?
Yeah, like the role of batteries is extremely important, and you see the battery is the future technology, and so many types of battery storage is being developed. With the battery storage system, we have to see what are our technical requirements. What are the technical requirements? Even the battery storage system is required for electric vehicles. Battery storage system is required in the renewables, even in the conventional power system. Even if you have, for example, small coal-based power plant, say 50 megawatt, can we think of the large battery systems like 50 megawatt to replace the coal-based power plant? Even this sort of things already start in several countries like Australia. So batteries may not be just like the small batteries being used in the renewables or maybe in batteries, but it can act like in the large scale, 50 megawatt, 100 megawatt. So for batteries, we have to see what is its technical requirements. And we have a large number of options, lot of development taking place in the batteries. Battery is the future technology. With batteries, technology changing very fast, cost is coming down, and we have several, options which can meet our technical requirement. Then we have to match this carefully and decide which type of batteries can be more suitable. I hope you got some understanding.
Okay, thank you, sir. Thank you, sir.
So any participants having any doubts? Otherwise, we'll wind up the session. Okay, sir. It's having once again. I thank sir. It's a very excellent presentation on behalf of Bvritn. Once again, I thank and immediately accept our invitation and deliver that. It's a very wonderful lecture to our participants. I hope all the participants are enjoyed the sessions, both the morning as well as the evening session also. Thank you, sir. Thanks.
So I would like to again thank you all the participants and organizing this short-term series of short-term. It has been really great for me to interact with the participants and organizing team. I wish you all the best. Extend my best wishes in the difficult time. So please stay safe and wishing you all the best. Thank you very much for everyone. All the best.
Thank you, sir. Thank you. Dear participants, the feedback link posted in the chat box, it will enable up to 4:30. Better to complete the feedback before 4:30. And another one, it's next session. Tomorrow the session will start at same time, 10 a.m. tomorrow. Thank you. The tomorrow resource person is Dr. Premalada Jana from IIT Roorkee. We'll meet on tomorrow morning. Thank you. Thank you, participants. And thank you, sir. Once again, thank you, sir.
कहाँ गया चैट बॉक्स जिसमें
एक मिनट चैट ये देखिए।
हाँ, ये हाँ निपटा दिया आ रहा बस इसी पे लिंक भेजी इसलिए कहा ना व्हाट्सएप पे नहीं भेजी।
अच्छा
ये रही ना ये आ गई भैया को पता चला वो टाइम रिकॉर्ड हो रहा है
ये देखा तो नहीं है ना?
ये था अरे सुबह वाला सुबह ही भर दिया जी मतलब सुबह का होगा नहीं लिखा वो शायद अपने पास खाली आया तो भर दो बस मतलब एक बार 2 बार भरो 4 बार भरो खाली हो तो भर दो जान दो क्या
और क्या मेरा 216 है ना।
216 नहीं तुम्हारा 13 होगा 216 मेरा है
213 होगा मेरा।
13 तो ऊपर होना चाहिए
Enter meeting, sir.
दो
13 है चार्ट में लिखता मेरे पास वो ऑटो फिल वाला तो डाल रखा है ना तो आता
Sir, what, sir? Enter meeting, sir. Host, sir.
How is the organization of Sttp? सही है ना?
मैं खत्म करता हूँ क्लिक करते हैं